So question 17, you've got a diagram here that shows the arrangement used by a student to investigate vibrations in stretched nylon string of fixed length L. Every time that the string is plucked, a frequency is measured, and the frequency is of the fundamental mode of vibration. And every time a mass is added, the string is plucked. Okay, so mass is added, string is plucked, a stationary wave is produced on this string, and a frequency of sound is produced, and that is measured. Okay, so what we've got as a set of results, three sets of results, three different masses added on, and three different frequencies produced. Now, in the first part of the question, it stated that the data and table are consistent with the relationship f is proportional to the square root of the tension in the string. So as the as the tension increases as a function of square root of t, the frequency increases proportionally. So how do we show that the data in this table is consistent with this statement here? Okay, so what we've got, we look at the table. F, there is the column for frequency, so we've got that data there, F. But we've also got data with mass, but not tension. So what we look here, up here, is the link between mass and tension. So this weight is hanging, so it has a weight of mg, and the tension in the string completely counters the weight, and you have that in a stationary position. So therefore mg, the downward force, is equal to the force pulling up by the string, which is the tension, is equal to t. Okay, so all I need to do is multiply the mass by 9.81 and I'll get the tension in the string. So that's what I've done here. I multiplied this column by 9.81 and I've got this set of values, and all of those values are in newtons. And then what I've done is I've square rooted it to get the square root of the tension, and that's the reason why I've done that is because the statement is the square root of the tension is proportional to the frequency. So I've got a set of data of square root of tensions. There we go. And we've got frequencies in this column here. Now what I'm going to do is I'm going to show that the frequency is proportional to the root of the tension. So if that is the case, then we can replace this proportional sign with an equal sign and a constant here. So frequency is equal to some constant k times by the square root of the tension to show proportionality. So where k is a constant. Now, if this is true for all of these values, then we should get the same constant each time. Okay. Now, how do we find that constant? What I'll do is this frequency, I'll call F1 because it's in the first row, divided by the root of the tension in the first row, which is that there. And the same for the second row, the same for the third row. They all should give me K as the constant, because if I divide by root T here, I will get F over root T, which is equal to that constant. So that's 110 divided by 2.21, which is the root of T, and gives me an answer for approximately 50. Same with 140 divided by 2.8, approximately 50. Same with 170 divided by 3.43, that's also approximately 50. So they all equal the same value, therefore the same constant. Therefore, we can show that we have shown that F is proportional to the root of the tension. Part B. So we've got a expression for the fundamental frequency of the sound that's produced when the string is plucked. It's equal to 1 over 2 times the length of that string between the two fixed points and multiplied by the square root of the tension in the string divided by the mass per unit length. Now, this is a derivation that you should be aware of to find the fundamental mode of vibration in a string that is fixed at two ends. And we got frequency, tension, mass per unit length, and the length of the string. So we know that the speed of a wave is equal to the frequency times wavelength. For the fundamental frequency, we know that the wavelength is 2 times by the length of the string. So that, if we remember that the picture that we often see for two fixed ends for the fundamental mode of vibration looks like that. The distance between two nodes is equal to half a wavelength, and that is the length of the string. So half a wavelength is equal to the length of the string for the fundamental mode of vibration, which is F0, and that means that the length of the string is, so 2 times the length of the string is equal to the wavelength, which is what we've written here. Okay, wavelength is 2 times the length of the string. That is the condition for the fundamental frequency and the relationship between length and the wavelength. So expanding this out, rather than I write wavelength here, I know that the speed is equal to the frequency, the fundamental frequency, times by the wavelength, which is 2L. Okay, so that is the speed, but we don't have speed here in this expression. We know that the speed is equal to the square root of the tension over the mass per unit length for stationary waves on a string. And now what we can do is we can equate these two, and we get 2 times fundamental frequency times the length of the string is equal to the tension in the string over the mass per unit length of that particular string, and rearrange to get F equals, and we end up with what we started off with there. And that's the derivation of the fundamental frequency of a stationary wave on a string. Next question is to find the original fixed length of the nylon string. We've been given the mass per unit length. So what we need to do is we need to rearrange this formula to get L equals. So L equals 2 times the fundamental, 1 over 2 times the fundamental frequency, multiplied by the root of the tension in the string over mu. What we can do is we can use the values from the table we've calculated. So let's have a look. What could we have got from the table? We could have got the frequency and the mass. So let's have a look. So we're going to put a value of frequency in. I've chosen 110. So let's have, we'll go back. 110 and a mass of 0.5. Okay, so 110, that's the fundamental frequency. So I'll put 110 there, 2 times 110. And then the root of the mass, remember the tension is equal to the mass. This tension is equal to mass times 9.81. So tension is equal to the weight. So that will be 0.5, which is the mass, times by 9.81. That's the tension in the string at a frequency of 110, divided by the mass per unit length, which is fixed. That's not going to change for that string, which is 2.25, 8 times 10 to the minus 4, which is put in here. And the length of the string between the two fixed points where the fundamental frequency is produced is 0.67 meters.